let's recall what we finished up with, which was theorem of Cauchy-Goursat. And we did it on triangles. It could have been done on rectangles. So we'll just say that we did it on rectangles, even though we did it on triangles. So if F is analytic on some rectangle R, and all points interior to it, then the integral of F around the boundary is 0. That was what we spent so much time getting last time. Okay. So in order to get Cauchy's integral formula, we're going to actually create a couple of different versions of this with weakened hypotheses. So like a slightly more general version will be we'll create a few slightly more general versions. So the first one is as follows: let R prime be obtained from a rectangle R by omitting a finite number of interior points. Finite number of interior points. Okay, so you start out with a rectangle, and you take out a finite number of points. It has a couple of it has some holes in it. Okay. And let's call those points zeta sub j. If at every point for all j, we have that the limit of f of z minus zeta j, as z goes to zeta j is 0. Then if let's say that f is let's say f is analytic on R prime. Okay, it's analytic on this set with the holes in it. So it's not analytic on the whole rectangle. Okay, it's analytic, but there are finite number of points where it's not analytic. Okay, but suppose that it satisfies at each of the points, it satisfies this condition. Okay, if that happens, then you still have the Cauchy-Goursat. Then it still turns out that the integral around the boundary of F is 0. So, for example, if your function is a bounded function, right? Your function is bounded, then as z goes to zeta, this is going to go to 0. This is finite, so you get 0. Suppose even if your function is not analytic, suppose it's analytic and it's bounded on you do this. Okay. So let's prove it. The proof suffices to show this suffices to show in the case of a single zeta, right? Obviously. So what we do is suppose this is your R, and suppose you have your zeta here. What you do is you put a square around zeta, centered at zeta. And you divide the rest of the thing into 9. You divide the thing into 9 rectangles. The one around zeta is a square, centered length. So, so let's say that R naught, this guy's R naught, square centered at zeta. Okay. Well, you know that then the integral over dr, the integral over dr prime of f is going to be just the same thing as the integral of dr naught. Right? Because from the previous thing, you know that the integrals over each of these boundaries is 0. Right? The integral over all of dr prime is going to be, you know, the sum over the integrals over these over these nine boundaries, right? And you know that, you know, 8 of them are 0, right? By the previous result. Okay. So we just need to show that we can make this thing as small as we like. Okay. So fix any epsilon, and let's say that we choose r naught so small that for all z on the boundary, we have f of z is smaller than epsilon over 8 z minus zeta. Okay. Convince yourself that's possible. Is that possible? Does that seem reasonable? Do you think that? Does that make sense? Do you think we can do that? We can choose an R naught so small that you're guaranteed that f on the boundary is controlled by epsilon over 8 z minus zeta. Why does this make sense? You're nodding. Why do you think you can do it?
Because the denominator can get really small. That's going to leave the right side to be large, but that doesn't really matter. There's going to be a maximum distance from z to zeta.
Right. So remember that it's a square, right? It's a square, so you know that 1 over z minus zeta is going to be bigger than 1 over the radius of the circle inscribed inside, say. Right. So you can make, as you shrink your square down, you're guaranteed that this thing is going to be bigger than some. This thing on the right hand side gets uniformly large, right? It's definitely going to be larger. Definitely going to be larger than 1 over r, right? And so further, you also know that that say if you started off with some initial square, that this is going to be bounded on that, right? So as you shrink it down, then you just have to choose it small enough that 1 over r exceeds the bound. Okay. So then what do you get? You get that this thing is controlled by epsilon times where, just in case you didn't catch this notation, when you write something like this, what we mean is the integral of the absolute value of gamma. Okay. And so, right, so you know that, right, okay, and then I should let you try this one. It's easy to see. See further that this integral here, this is sort of the same, along the same lines, is smaller than 8. Why? Can anyone? Shall I let you try it as an exercise? Why would this thing be smaller? Well, you have the same sort of thing, right? 1 over. I'll let you try. Try for 1 or 2 minutes to see to get this bound.
Easy.
His rationale. I know it's based on ours. It was good. I'm just gonna.
You can get
No, that's it.
okay, I think that's probably an important piece of it.
So now I'm assuming it just like coming out of this.
Yeah.
Somebody have an idea?
Can you explain that the earlier step below that inequality?
Yeah. So right. Right. As you shrink your, so the intuition, right, is that as you shrink your rectangle down, then this is going to become arbitrarily large, right? So further, you know that Hold on. I was lying, right? I was lying. Like, earlier I said that it's bounded. It's actually, I was saying that it was bounded on some set here, right? But that's just actually not true, because that point in the middle is your That point in the middle is your zeta, right? The thing is analytic, but not at zeta, right? So what we need to use, I guess, is this fact, right? I think. Right. Right, because you don't know that your function is continuous. In fact, right? You don't know that your function is continuous at that point. If it were, then we'd be done. Right? Yeah.
What does the analytic have to do with f of z being bounded?
If it were analytic on the whole, if it were analytic on the whole on the whole square, then it would be continuous, and so it would be bounded. Right, but we don't know that.
I don't even see the continuous mean that it would be bounded.
Oh, analytic means that you're continuous, right?
Right.
Or it implies that you're continuous, and you'd be continuous on a compact set,
Okay.
right? So then your image is compact,
Mhm.
and that's bounded. Right. Okay, but that's actually not quite what we need. So let me think. So why can we do this? Choose R not so small that this happens.
We can move the z minus zeta over, right?
Ah. Exactly. Thank you. Yeah. Move the z minus zeta to the other side. We know that the limit is 0. Right. Thanks. Yeah. So that's why.
Why the 8?
Oh, you'll see in a second. Oh, the 8 is to get rid of that, to cancel with that 8.
Oh, okay.
That we get later. Okay, great, thanks. Okay, so is this easy? Is this easy? I think it is. No, it actually is easy. I hope. Okay, so well, we have a square again. Right? We have a square again, and again, suppose there's a circle inside here, right? So we know that z minus zeta is bigger than r and smaller than some number times r. It's certainly smaller than 2. Okay. So right. So 1 over v minus zeta is smaller than 1 over r. Right, that's why I put the 2 over here, because it was wrong. So this thing is smaller than 1 over r. So you know that this thing, z minus zeta, is smaller than 1 over r times this. Right? Right. And then this is just the perimeter of your square, right? Which is 8r. So 1 over r times 8r. Okay. So what do you see? That I'm sorry, I missed the 8. There should be an 8 here, right? So this thing is smaller than epsilon over 8. Epsilon over 8 times this thing. This thing is smaller than 8, and so we get that the whole thing is smaller than epsilon. Sorry, I missed the consistency. So the whole thing, you can see, is smaller than epsilon, and epsilon is arbitrary, so you get 0. Elena, what is it? Do you have a question?
No, I was just.
You can't see. Can you see what?
Yeah, I can see it.
Okay. Okay. Any questions? Okay. So it's okay to be analytic except for a finite number of points, as long as we have this. later we'll see that this actually forces the thing to be analytic anyway. So in some sense, we don't need to do it. Everyone all right? Everyone all right? Except for me. Okay. Okay. So now we're going to do Cauchy-Goursat on a disk. So if F is analytic in an open disk, delta, then for every closed curve gamma in delta, the integral over any curve, closed curve in the disk is going to be 0. So I mentioned last time that maybe one way you could do this is to approximate paths by polynomial paths. I'm not sure. I'm actually not sure if there may be some difficulty with that. So our book and other books. The book, one book I know does it that way, but it doesn't say how to do it. It just says it's possible to do it. So our book and other books tend to go this route. So let's go this route. It suffices again to show there exists an antiderivative, right? That F has an antiderivative. Okay. So what you do is sort of the same thing we did before. Fix a point Z0 in delta. Okay. And then for an arbitrary Z in delta, we let f of z be defined as the integral over some path sigma of f, where here's how we're going to do it. We have a disk, we've fixed the point z0, and what the path sigma that we're going to take is going to go horizontally first and then vertically. So sigma consists of a line segment from x naught y naught to x comma y naught. Right? So you fix y naught, and go across to x comma y naught. Right? So this is z is xy, z naught is x naught y naught. You go across to x y naught, and then you go up to x comma y. And then followed by 1 from xy naught to xy. Okay. Today is Chinese New Year. Happy New Year. Long time ago, I would make kind of a New Year's cake, and bring it in, but it's impossible with 3 children. My wife was already angry enough with me yesterday.
How did you know?
I think it was obvious. But it's not clear. You're right. I'll just pretend that she was happy. I'll just believe she was happy. The advantage of not knowing other people. Okay. Okay. So yeah. So I don't know. Maybe if I have time, I'll make a Lian Gao and bring it in. Anyway, yeah, but no money for you guys. Okay, so yeah. Anyway, okay, so this is going to be our antiderivative. So let's find something. Delta f, the partial this time with respect to f, with respect to y is I of c. Turns out to be I of c. Right? Why does that happen? We take the partial with respect to y. Well, that's the partial with respect to y of two things, right? First, we've got this integral of the guy from x naught y naught to x y naught, right? But that thing doesn't depend on y at all, right? So we can ignore that. We can ignore that part of it, right? So we're only going to look at the partial of the integral from y naught to y of and t again. Right, so there is this thing here. There is something else here. Right, there is some other integral here, but it doesn't matter, because it doesn't depend on y. So where gamma of t is x plus I, and t ranges from y naught to y. Okay, that's the path. Okay. Well, then you just do a calculation, right? Gamma prime. Prime t is I, right? And so you get I partial y naught y f prime t dt, right? But then you use the fundamental theorem of calculus. Right? Fundamental theorem of calculus says that if you're differentiating some integral, like this, right? This sort of area integral, then all you do is you evaluate this thing at you evaluate the thing at y. And so you get I f at gamma y is c. Yeah, Chris.
Just to go back, why does it suffice to show that f has the antiderivative?
Because if it has an antiderivative, then you know that you can use the fundamental theorem of calculus on it. And you get, remember the path independence theorem, right? Having an antiderivative is equivalent to satisfying the closed loop condition.
All right.
Okay. Okay. Everyone okay with the calculation? Okay. So now we do something funny. Using the rectangular Cauchy-Goursat, we can switch the path sigma for a different path. This path, let's call it sigma prime. Okay, right? Because you know that the integral over this whole thing is going to be 0, right? So this integral and this integral, we don't have independence of paths for arbitrary paths, but we do have it for guys that go around a rectangle, right? Because we have Cauchy-Goursat for the rectangle. Okay, so right, the integral around this whole thing would be 0. So this integral, this integral, these integrals are the same. Right? So we switch it for sigma prime, where sigma prime is this path. Now, by a similar calculation, partial of f with respect to x using this form. So taking the derivative of it on this form will make it just as obvious that the partial of capital F with respect to x is also f of z. And so what you get is that I partial of f with respect to x equals partial of f with respect to y, which is the Cauchy-Riemann equations. And further, your partials are continuous. Your partials are continuous functions, and so we can invoke our theorem, our converse theorem, that as long as your partials are continuous and you satisfy Cauchy-Riemann, then you're analytic, right? So it'll tell you that f is analytic, and further, prime is little f. So we found the antiderivative. So just remember the theorem. Okay. And then all right? Yeah.
Why, if we knew that there f had an antiderivative, why don't we know that over any kind of arbitrary closed path with the?
Now we do.
Oh, I mean, so we can't assume since we already proved that.
No, we only did it over a rectangle.
Well, I mean in the previous proof, but just the properties of contour integrals. Isn't that one that it?
What we showed was that integrating over, and we did it for triangles, but pretend we did it for rectangles. What we showed was that integrating over a rectangle gave you 0, but we didn't show that integrating over an arbitrary loop was 0. If we had, then we would know automatically that you had an antiderivative.
So we had that before.
Yeah.
No.
Oh, we didn't know we had an antiderivative? Just, I thought.
No.
Oh. Wasn't that how you showed evaluated the integral using the fundamental theorem of calculus? Or is that not supposed?
No, right. Yeah. I mean, this is.
I guess you don't necessarily need.
Yeah, this isn't a complex antiderivative.
Okay.
Right. Here you're integrating a continuous function. Right. You're integrating a continuous function over a real interval. Right. And then you're differentiating with respect to that real interval. And so the calculus, fundamental theorem of calculus, is what we're using here to get
That is replaced. Okay. But so now that we know that there's an antiderivative that exists, now arbitrary path, we would know that
inside of
arbitrary
this.
path.
Yes, inside of this.
Inside, yeah. But if there's a circle within this.
Yeah, yeah. So as long as it's inside a disk, we're okay. So you have to think, what did we need? What was the feature of the disk that allowed us to do this? And it was that whenever we went this way, we could also go this way. Okay. So if you had something like this, however, then you'd be in trouble, right? Because you could have, suppose this is your z and this is your z. Okay. Then you're not guaranteed the opposite sign, and so you can't play this argument. Okay. So if you have, for example, this works. In particular, this will work on a convex set. Right? If your set is convex, or I mean, just think, if your set is like elliptical or something like that, then it's okay. But if you have any sort of dents into it, then you're in trouble. Yeah, so you have to have this property that whenever you have half of a rectangle, then you have also the other half in your set. As long as you have that, then the argument goes through. Okay. Right. So now that gives us Cauchy-Goursat inside of a disk for any loop inside of a disk. Okay. Any loop in the integral is going to be 0 because we know that inside the disk we have an anti-interlude. Is everyone all right? Yes, you are. No, you're not.
Is the
Yes.
drawing to the right, is that supposing that it's centered?
Which, this drawing?
Yeah.
What is centered? The
Like
xenon?
the square. Because can't you have like 2 points and have like an L-shaped path from 2 points in a disk, and the other half would go outside of the disk if you're on the edge?
Like, so you shifted Z naught up into the left.
Yeah.
Oh. Yeah. Yeah. So, there are a lot of these things.
Is this not centered at Z naught?
Maybe, let me think. Yeah, maybe you have to choose. Yeah, I guess you have to choose Z naught to be the center. Yeah. If you choose Z naught to be the center, then that's not going to happen. Yeah. Thank you. Maybe I should just let you guys teach the class. Yeah. Okay. Yeah, thanks. So, there's one more thing, one more extension of Cauchy-Goursat. Goursat, the FB analytic in a region delta prime obtained by omitting a finite number of points, say the J, from an open disk delta. Again, you have similar to the result from preceding the previous one. If this equals 0 for all j, then the integral over any closed curve is going to be 0. Okay, so this is sort of the final version that we're going to use of Cauchy-Goursat. And I'm not going to prove it. Maybe I'll let you. I'll put it as an exercise, but maybe as a bonus exercise. So you can try it. You have to do some. You have to sort of combine the argument. So, I'm going to talk a little bit about path deformation. Path deformation. But I think I'm not going to. I think I'm not going to give the proof because the proof is long, and I don't think it's long. And further, the proof given in the book, they say, is not actually the full proof. They say they give this long proof, and they say actually this is not the full proof. Go look online for the full proof. We've got it on our website in case for those who are interested. So I'm just gonna tell you how it works. I'm gonna tell you the statement of the theorem. So here we go. Let me see if I can describe what's going on. So let I be 0, 1, the unit interval. We're going to describe a notion called homotopy, path homotopy. So it's when you have two paths and one path can be deformed into the other path. Okay. So you have something like you have one path like this, and you have one path like this, and you can slowly, in a continuous way, change one path into the other path. Okay. And what the result will be is that if your function is analytic on this region, on this whole region, then the integral over the paths are going to be the same thing. Okay, so you can deform paths without changing the integral. Okay. Similarly, there's going to be another result. If you have a loop and you can sort of expand the loop into another loop, then the integral, and if your function is analytic on this region, then the integral doesn't matter. I mean, the integral doesn't change. Okay. Okay. So that's the idea. Okay. Let's make it. Here's how we make the idea precise with some definitions. So you have these two curves. So you have these continuous curves in omega. Okay, such that gamma of times 0 is gamma 1 of times 0, right? They share the. Let me say it this way. Gamma 0 and gamma 1 share the same initial point. C0 and final point C1. Okay. If there exists a continuous map H going from the unit square into gamma, such that H of 0t equals gamma 0t, H of 1t equals gamma 1t, right, for all t in 0, 1. And H of S0 is Z0, and H of S1 is Z1, right, for all S in I. And we say gamma 1 and gamma 2, gamma 0 and gamma 1 are path homotopic. Path homotopic or homotopic with fixed endpoints. Homotopic with fixed endpoints. So the picture is this. You have a map H going where, so this is S and this is T. Okay, right? Gamma 0t I'm sorry, h0t. So when s is 0 and you let t vary, then it describes gamma 0t. Right? So here's gamma 0, and here's gamma 1. So this is z0, and this is z1. Right? As you go from here to here, you go from here to here. Right? So along the left edge of it, along the left edge, it looks like gamma 0. Okay. And then along the right edge, along the right edge, it looks like gamma 1. And in between, you get these intermediate paths. Notice that you're requiring that that all of these intermediate paths start at z0 and end at z1. Right? They all start at z0 and end at z1. That's this condition. That all the intermediate paths start at z0 and end at z1. Okay, so they all have the same endpoints. Okay, and so if you have a continuous way of moving from one path to the other path, then we say that they're path homotopic. They're homotopic to each other. Okay. Question?
Yeah, you wrote z0 twice.
That should be z1. Okay. Okay. Second notion. Again, you have these curves, right? Continuous curves again. But this time you don't have any control over the endpoints. So now, if there exists continuous h going from I cos pi to omega, such that, well, again, h of 0t is gamma 0t, h of 1t is gamma 1t, and you have this condition, h of s0 equals h of s1. This condition just ensures that all of the intermediate guys are loops. All loops. Okay, sorry, these guys should be loops. Continuous closed curve. Okay, so you have two closed curves. Right. You have two closed curves in your space. Right? And suppose there's a way to deform one guy to the other guy. Then we say they're homotopic as closed curves. Then we say gamma 0 and gamma 1 are homotopic as closed curves. So if your omega had a hole in it, right? If your omega had a hole in it, then you wouldn't be able to do this, right? You wouldn't be able to deform this path into the other path. Okay. So the homotopy, being homotopic to each other depends on the domain. Right? So just as a side remark, this gives us the actual definition of simply connected. If omega in C is connected, and every curve, every closed loop is homotopic to a point, in omega, then we call omega simply connected. Okay, so this makes rigorous the notion we mentioned earlier about being able to take a loop and then deform it down to a point. What we mean is that there's a homotopy between your loop and the loop that just stays still at one point. Okay. And if that happens, then we call the domain simply connected. So I'm just
One more time. Did H have to be continuous or differentiable?
continuous. Okay. So now I'm going to state the deformation theorem. I'm not going to prove it. If F is analytic on an open set omega, and gamma 0 and gamma 1 are piecewise C1 curves in omega. If gamma 0 and gamma 1 are homotopic, then the integral of f over gamma is going to be the integral of f over gamma 1. So either with fixed endpoints or as closed curves. So we're going to leave out the proof because it's long and elaborate. It's possible to give sort of a hand wavy type proof. If you suppose you have two loops, gamma 0 and gamma 1, gamma 0 and gamma 1, and you want to show that the integral over gamma 0 equals the integral over gamma 1. Right. Well, you can cut a line here, like this. Right? You cut a line and you say, well, I know that if I integrate over this upper region, I get 0. And if I integrate over the bottom region, I get 0. Right? But then you add those things together and you see that shows you that the integral over gamma 0 equals the integral over gamma 1. So there's sort of a hand wavy proof, but apparently to give the full power proof requires some work. So, right. Do you see how this? Does everyone see how the hand wavy proof works? Right. You have these two things. Right? And you say, well, I know that if I integrate over this thing, I get 0. Right? And I know that if I integrate over this thing, I also get 0. Right? So that tells me that the integral over the upper guy plus the integral over the lower guy is 0. But then you notice that the integral over the upper guy plus the integral over the lower guy, if you break it down into pieces, gives you the integral over the open loop plus the integral over the inside loop in the opposite direction. Right? So that tells you that the integral, let's call this one gamma 0 and gamma 1, the integral over the outside guy plus the integral of the outside guy plus the integral of the inside guy in the opposite direction is 0. Right? But that means that the integrals are equal to each other. Okay. So that's the sort of maybe unrigorous way of proving path deformation. Yeah, question.
Why do you know that the halves themselves are, if you integrate over those boundaries, you get 0?
Well, because the function is analytic on the set, right? So you know that integrating over a closed loop is going to be 0. And your function is analytic. Right? in your function's analytic, so integrating, I guess you have to assume that it's inside a disk.
Oh,
But, yeah, make sure it's inside a disk. Okay. So, let me see if we can get to Cauchy's integral formula. Okay. So Cauchy's integral. So first off, let's recall a calculation that we did earlier. For any circle around some point z naught, remember we did this calculation. It was just any circle gamma around c naught. Right? We got 2 pi I if we went around went around it one time, right, in the counterclockwise direction. So I'm going to sort of expand on that idea. Suppose you have a z naught in C, and let gamma be piecewise C1 closed curve, closed loop that does not intersect C naught. Okay. Then the integral of this is going to be a multiple of 2 pi I. So here's the proof. It's kind of a cool one. Let h of t be the integral from a to t of gamma prime s, gamma s minus z naught ds. Okay. So you're going to integrate this thing over so let's say let's say the domain of gamma is alpha beta into x. So it's alpha here. So you're going to integrate on this real integral. Notice that h is continuous on alpha beta. And wherever gamma prime is continuous, h is differentiable. With h prime of t, just going to be gamma prime of t over gamma prime of t minus c naught by the fundamental theorem calculus. Okay. A calculation. If you differentiate with respect to t, e to the minus h t gamma t minus z naught, you get 0. It's just, you just use the product rule and the above observation. Okay, so it's easy. Okay, so so you have a function. So this function is continuous. Right? It's continuous and has derivative 0. So it's constant. Right. So then plus e to the negative ht this minus z naught equals e to the negative h alpha gamma alpha minus z naught. Right? Because it's constant. So it's going to be equal to its initial value. Okay. But h of alpha is 0, right? So this is just 1. Right? H of alpha is the integral from alpha to alpha, and so that's 0. Right? And so you end up with e to the ht is going to be gamma t minus z naught over gamma alpha minus z naught. Just by arithmetic. Now, that tells you that e to the h beta is gamma beta minus z naught over gamma alpha minus z naught. Right. So take t to be beta. Take t now to be the right endpoint. Right, and you get this. Right, but gamma is a loop. Gamma is a loop, so this equals 1. Right, gamma of alpha equals gamma of beta, so this equals 1. Right, and so you see that e to the h. So you see that h beta, right? That's to say this integral. Is a multiple of 2 pi. Okay, which is what you wanted to show. Yeah, Christian.
Isn't h of beta 0 right here?
H of beta.
Except e to the h of beta is 1, and h of beta must be 0.
H of beta must be 0 or some multiple of 2 pi I. Remember, because of the what? Because you can right, e to the 2 pi I is also 1.
Oh,
e to the
okay.
4 pi I. Remember, that you can get 1 if and only if the exponent is some integral multiple of 2 pi I. Sorry. Yeah. So h beta is 2 pi ki for something. So so that's kind of interesting. We have this what we see is that if we integrate z minus z naught over any path gamma and divide that by 2 pi I, then that's always an integer, right? That's what we just showed. The lemma says this is always going to be an integer. We call this integer, we call this n gamma z naught, the winding number of gamma around z naught. Okay. So it actually tells you how many times the loop goes around z naught in a counterclockwise way. If it's a negative number, it tells you how many times it's gone around in a clockwise way. Okay. So yeah. So this thing basically counts the times you go around. Now we have 2 minutes, and maybe I think I can do it. You think it's impossible, but in fact, I think we can give you the Cauchy Integral Formula. Okay, so here we go. Let F be analytic on an open disk delta, and gamma be a closed loop in delta. Say let z naught be any point not on that loop. Then and the winding number times the value of the function at z naught actually equals 1 over 2 pi I. Gonna collapse. From excitement or exhaustion? Which is it? Let's say it's excitement. Why not? Then the winding number times the value of the function is expressible as this integral. Okay. In particular, if your winding number is 1, then you have your function expressed as this integral around a loop. Okay. So this gives you the value of your function in terms of the value of some integral around a loop that may be far away from your point. Okay. Let me give the proof. You can do it. So, let capital F of z be f of z minus f of z naught over z minus z. Okay. Note that f is analytic for any z that's not at z naught. This thing is analytic except at z naught, and at z naught we see that the limit of f of z times z minus z naught, as z goes to z naught, is just the limit of f of z minus f of z naught as z goes to z naught, which is 0. Because little f is analytic. So we can use the Cauchy-Goursat theorem, the last form of the Cauchy-Goursat theorem on capital F. So Cauchy-Goursat implies that the integral of this guy is 0. Right? But if you separate that out, it says that the integral of fz over z minus z naught dz equals f of z naught times 1 over z minus z naught dz. Right? And what's that? That is f of z naught times 2 pi I times the winding number times the winding number. Okay. And so you get the formula. Divide both sides by 2 pi I, and that's it. Okay. So I was 2 minutes late, but I think this clock is fast. Okay, so that gives you a formula. Let me just write it in a slightly different way. If I write like this, f of z is 1 over 2 pi I f zeta zeta minus z d zeta. This is how people often write it. To emphasize that you can express your function at any point, right? You can express your, assuming that the winding number is 1. Okay. Assuming that the winding number is 1, if the winding number for all your points is 1, say, suppose suppose your z is inside a circle. Your gamma is some loop like this. Well, then you've expressed for every point inside the circle, you say that f of z can be realized as this integral on the boundary, right? So that is the boundary values of your function determine all of its interior values. The boundary values of your function, if you know the boundary values, if you know f on gamma, then in fact you know f at every single point on the interior. That's kind of shocking. Okay, that's the Cauchy integral. And this is the great tool that we're going to use to do everything from here on, or for a lot of things from here on.